Record.
So
It's recording.
yeah, welcome to the so you can start maybe. So yeah, I think yeah, this is the 9th week of the I categories reading seminar, and today I'll be talking about the Joyal model structure. So yeah, so we'll begin. So here's the plan. So I'll first I'll kind of give a quick recap of a few things that we have already seen. So kind of so a bit of a recap. Then we'll talk about categorical equivalences. So yeah, it's pretty straightforward. So maybe let me say this. So yeah, so maybe it's not sections 3.3 and 3.4. Maybe it's because in the previous talk, Heiko talked a bit about join and slice construction. So I think yes, kind of sums it up. So yeah, so let me start by pointing out that so people would have guessed it by the kind of things that I'm about to talk about. It's not a classical construction that I'm about to talk about. So because a classical construction is something that like most people are familiar with. So this is the construction that I'll be talking about in this talk. So this is due to Danny Stevenson, and maybe I can link the paper some other time. So yeah, after categorical equivalences, I'll talk about Dweck-Kahn equivalences, and then kind of show that equivalences are in fact Dweck-Kahn equivalences. Then I'll talk about pre-fibrant simplicial sets, and then about the Joyal model structure. So yeah, let me start a bit by a bit about the motivation of Joyal. So Joyal basically realized that there's a primordial model structure on the simplicial sets with infinity categories as the fibrant objects, right? So that was kind of the motivation, right? And that's right. And so again, I should say this before that. So most of the things can be, so my major references are Topos theory and Joyal's. So let's recall. Let's begin. So I'll talk more about that, other things later. So let's recall. Wait. So first we'll start by recalling the homotopy category. Recalling what homotopy category is. So we have So let's recall that we have the functor. So I don't know, we call it or we call it whatever you want. That takes a simplicial set to the homotopy. So this is I don't think I need to talk more about it because we've already talked about that before. So maybe begin with the definition. So an edge in an infinity category, so let me call it C, is called an equivalence if the image in the homotopy category, it's an isomorphism. So this is an isosceles. So that's the definition of an equivalence. So more generally, let me say this. More generally, we can replace C by simplicial set. Right. So and then you will have an equivalence. We can more generally think of it in terms of simplicial sets. So now, let me define an equivalence of an infinity category. Maybe Okay, so let me call my infinity categories to be C and D. C and D be any category. A map comes to D is an equivalence so this is just kind of another definition that you have. Equivalence if there exists a map sorry, so yeah, I'm kind of not very used to the setup. So I'm sorry for this. Such that there exist equivalences in the infinity categories. So, right, in the infinity category. So yeah, functor categories. Right. So, okay. So now let me introduce some notation that is yeah. So as I said before, as I've said before, that the construction that I'm about to talk about. So yeah, the construction that I'm talking about. So that is not the classical construction. So we'll see. We'll leave this. So let me introduce some notation from so yeah, this notation basically it's from I found the notation in it's in Duggar and Spivak's paper. That is, so yeah, I'll maybe send a link later. But yeah, let me introduce the notation. So F and G are morphisms in the category of simplicial sets. So just give me a moment. Yeah. So, okay. So we have these maps in simplicial sets. So yeah, they are J homotopic. So now I'll define what J is. So yeah, I think I should do that before, but yeah, let me write the definition first, then I'll define what J is. If there exists a map, so I think somebody should make sure I'm not writing this wrongly because this is from my memory. So hope this is not wrong. Just that. So when you compose H and IO, so yeah, I think I'll define ION. So there's another I that I'll use. F and Joyal is equal to G, where so IO and I1 are obvious inclusions. Right. So now, yeah, let me define what J is. Yeah, let me pause for a second. Let me make sure I'm not thinking about this wrongly.
I think it looks right.
Sorry?
It looks right. The notation.
Yeah, no. Yeah, that's right. Yeah, I'm kind of thinking about it. Thinking about the J. So yeah, let me pause for a second. I'll make sure. Sorry for this, but I think this it's about right. Yeah, I thought for a moment. So yeah, so this is yeah, okay. Let me write this. So that there's no confusion. So J. So yeah, J denotes. Yeah, so yeah, I kind of thought for a moment. Yeah, there was something that I'm not sure, but yeah, I think this is right. So J denotes the groupoid. J denotes the groupoid interval. Right. So yeah, so what do I mean by the groupoid interval? So it is basically the groupoid with objects 0 and 1 and a unique iso between them. Right. So yeah, so that is what I mean by J. And okay, let's move on then. If you can, I think I'll have to pause for a moment. Yeah, I'm sorry. So yeah, so wait, where was I? Right. So I defined what it means to be, yeah, what it means for two morphisms to be J homotopic. Right. So let me make a remark now. So this is what I'm thinking of right now. Right. So wait, sorry. So right. So this map is an equivalence of infinity categories if it's a J homotopy equivalence. So what do I mean by that? So maybe yeah, in sense that there exists a map. So let me call it say F prime D to C. Yeah, I hope yeah, it's C and D. So yeah, I hope I don't get that wrong. So yeah, D to C says that FG and GF are J homotopic to, right? So the identity maps, right, are J homotopic to identity T. Right. So yeah. So now let me state a lemma, an important lemma, or maybe a proposition. I don't know. So yeah. So let's consider homotopy equivalence. So let F from say K to L as a homotopy equivalence where wait, yeah, I'm sorry, this got overboard. So yeah, let me get rid of this. Right. So yeah, where these are Kahn complexes, where KL are Kahn complexes. This is my category of Kahn complexes, which I think I have defined before. So yeah, so they're Kahn complexes, then F is an equivalence of infinity categories. Right. So I think, yeah, this is, so yeah, I want to give a proof. I mean, this is obvious because yeah, everybody knows that. So yeah, let me call it an edge. So every edge in a Kahn complex is an equivalence. So yeah, it kind of is obvious. So yeah. So now finally, let me define categorical equivalences. So okay. So I think I can get rid of this. Sorry. Categorical equivalences. Okay. So the definitions due to Joyal. a map from A to B of simplicial sets where A, so yeah, A and B are simplicial sets. I'm sorry. So, not used to working with a drawing tablet. Right. So yeah, of simplicial sets is a categorical equivalence if for any infinity category. So let me call it Y, infinity category Y, the map so yeah, this map is an equivalence of infinity categories. Is an equivalence of infinity categories. Right. So yeah, so this is what I mean by categorical equivalences. So right, so yeah, there's another proposition. There's an important proposition. So again, if you are taking, so yeah, if this map is an equivalence between infinity categories, then yeah, so then it is a categorical equivalence. So yeah, I won't give a proof of this, but yeah, I'm just going to prove by some. I think yeah, you can prove this by some jointness arguments. So yeah, so now the lemma that I'm stating. Right. So a map of again of simplicial sets. So let me call it F from A to B is a categorical equivalence. If F is, oh no, I don't think this is the right way to put it. So yeah, I should say that if it is a, so if it is an inner anodyne map, so yeah, if it is inner anodyne, so we've talked about anodyne maps before, is inner anodyne. If so, if this map is inner anodyne, then F is a categorical equivalence. So again, for the yeah, but this time, yeah, I think I don't remember the section exactly, but yeah, you can find the proof in Idopus theory. I think this is in 2.3 point something. I don't remember exactly, but yeah, this is in 2.3 that I can remember. So, right. So, okay. So, not the lemma. So, if G next to Y is an acyclic vibration, then G is a categorical. Again, I won't give a proof of this. So yeah, maybe a remark that I would like to add, that is the class of categorical equivalences in the category of simplicial sets is stable under filtered colimits, and we've talked about what it means to be stable under filtered colimits before. Stable under filtered colimits, right? So just remark. So now Okay, so now, now we are in a position to define the Weyerkon equivalences, which I'll refer to from now onwards as DK equivalences. Right. Right. Okay. So yeah. So let me think. Yeah, let me pause for a second. And yeah, so let me, maybe I'll start like this. So suppose X and Y are objects of some C is your C is an infinity category. Infinity category, and X and Y are objects of C. Then so there exists a mapping space, right? So there exists a mapping space of morphisms which in fact, let me add this. So it is in fact a well-defined object in, okay, so let me maybe write that in brackets. Well-defined object of the homotopy category of the category of spaces. Right. Okay, cool. So let me give a definition. So suppose S is a simplicial set, and so X, Y are vertices of S, right? Then maybe I should write this. So I'm defining left morphisms. So so for a simplicial set X, S, and if you have if you have vertices of S, then right, then the simplicial set. So let me denote it like this because these are left morphisms, and we'll get to why they are called left morphisms in a moment. The simplicial set is of left morphisms from X to Y in S is the simplicial set whose set of n simplices is the set of all maps. So I think this is, I think that's right. With, so I kind of get confused about this sometimes, whatever. So with this being X, and so if you just, this is the constant, and this gives the constant and simplices on vertex Y. Right. So maybe I'll just say this: the face and degeneracy maps are like, they are defined in the obvious way. So you can maybe refer to HTT again for the details, but I won't get into that. So maybe a remark. Right. So if C is an infinity category, then the simplicial set of left morphisms, the simplicial set of left morphisms, right, is a Kahn complex presenting the mapping space that we talked about. Right. Okay. All right. Okay. All right. Yeah. So there's something interesting that happens. So maybe I'll just say that. So yeah, if okay, so let me write this. So yeah, so yeah, this is like in a way you can call it the naive mapping space. So basically, right. So if you have a simplicial set, so S is a simplicial set that presents an infinity category, right? So let's think about it. So this presents S presents C, right? That is, which implies that there exists categorical equivalence. Then this simplicial set that I'm calling for brevity the naive mapping space. This may have a different homotopy type than the mapping space that we have, right? So, right. I don't know if I should talk about what a homotopy type is, but I don't know. So yeah, I think everybody's familiar with that. So yeah, maybe okay. Let me say this. So this is the kind of way you can think about it. So yeah, I'm saying this because this is related to, so this kind of a way of thinking about homotopy types is related to higher topos. So just because it's higher topos. So yeah, let me just say this. So like, so the thing is that, so you think of every object in an infinity one topo, right? So you think of it, so yeah, so maybe I can give a few examples also, but I don't think that's worth spending a lot of time on. So let me just say this. So every object in an infinity one topos, right? So it is a homotopy type in the world of that infinity one topos. So this is kind of a way to think about it. So this is the homotopy type in the world of that infinity one topos. So yeah, I think you can find more about that in the NLab page. Like, yeah, right. Like objects in an one topo. So what do I mean that it is a homotopy type in the world of that infinity one topo? So this is similar to the fact that objects in a one topos, they are like they are like sets in the world of the one topos. So that's the way to think about it. So that's kind of a neat way that I find to think about homotopy types. But generally, yeah. So I think of a homotopy n type as an n truncated object in infinity one category. And so yeah, we can maybe talk about that more later. Not now. So right. Okay. So yeah, so now let me define DK equivalence. So DK equivalence is diachronic equivalence. Okay. So A, B are infinity categories. So a map. So let me call it G. Map from A to B is so there are two things for a map to be diachronic equivalence. There are two things that we have. So it is essentially surjective if if you just pass on to the homotopy categories. Right. So this is also essentially, so let me shorten essentially to this. Essentially surjective and surjective to this is essentially surjective. What do I mean by essentially surjective? So it is like right. So it is surjective on objects up to an isomorphism. So that's the way to think about it. So that's what I mean when I say essentially surjective, right? So let's move on to the second condition. So yeah, so it is fully faithful if this is standard stuff. So I need to make sure that I don't mess up my notation. If I do, please let me know. I hope I don't. So okay, so Let me call them K and K dash. Right. So for every vertices, right? Yeah, the vertices. Right. Right. So now if F is fully faithful and essentially surjective, yeah, I'll use this quite often. So let me, yeah, as I said, let me shorten it a bit. So if F is fully faithful and essentially surjective, then F is a Dwyer-Kahn. Let me write this because it's a definition Dwyer-Kahn equivalence. Let me write this. Right. So yeah, so now we'll be working towards justifying something. So let me write that as a claim before we move on. So the claim is that right. So a map between infinity categories is an equivalence if and only if it is a Dwyer-Kahn equivalence. So this is one of the key steps in the construction that I'm talking about. So yeah, so that is equivalences are Dwyer-Kahn equivalences. So let me write the claim. So a map between infinity categories is an equivalence if that's a DK equivalence. So I think I should stop right now and put my laptop to charge for a moment. Bye. Sorry. Okay. So yeah. This is the claim. This is something that I'll be working on. And yeah, so yeah, I won't fill in all the details, of course. So you can refer to Joyal's notes and high topos theory for most of the results that I'll be talking about. So if this map is an equivalence, so this dilemma is an equivalence between infinity categories A and B, then F is fully faithful. So yeah, so you kind of move stepwise, right? In order to show that you have a bidirectional implication. I mean that, yeah. So they're one and the same. Right. So now we want to prove that DK equivalence is a categorical equivalence, right? So yeah, so let me write this. So an inner vibration between infinity categories. So let me call them X and Y. And let me call this map F from X to Y is a categorical vibration. So now I define the notion of a categorical vibration. If so, we just pass on to the homotopy category. So it is an isovibration. We've talked about isovibration. Oh, but yeah, I can maybe talk about that. But yeah, so we've talked about it. So maybe a remark that I'd like to add. This is something important. Also, we'll realize that this is important in the construction of the Joyal model structure. An inner vibration. An inner vibration. So you can call it P instead of F. From A to B is a categorical vibration if it has a right lifting property with respect to the inclusion, this inclusion that we have, and I defined what J is, the groupoid interval, right? So this is an alternate way to think about categorical vibrations. So like this. Right. So, okay, now there's a lemma that I'll prove that I feel is worth proving. So again, this is due to Joyal. So if we take a categorical vibration, so let me again call it P to B. If there's a categorical vibration between infinity categories A and B, so right is so yeah, if it is fully faithful and essentially surjective, so then it will be an acyclic confirmation. So yeah, essentially surjective. So maybe I should have taken the short form. Okay, anyways, so then P is an acyclic confirmation. So yeah, I'll give a proof. And yeah, this is Joyal. Right. So suppose P is fully faithful and essentially surjective. Right. So what does that mean? So that means that P has a right lifting property with respect to this inclusion that you have. J is the group-wide interval. Right. So right. We'll pause for a moment. Right. See. I think so I think yeah. Right, I think that's right. So that implies that P is surjective. Right. So maybe I'll write that. But yeah, that implies that P is surjective. Yeah, I think that's right. Anyways, so right. So what do we prove? We prove that for n greater than or equal to 1, the following diagram, right? So yeah, the following commutative diagram, so it has a filler. So to draw that. So it's B. Oh, it should be. And right. So yeah, it has a diagonal filler. And now, right. So I won't go to the details, but by adjointness arguments, yeah. So it is equivalent to show that. So you have the following. Yeah. So let me draw this first. So again, as I said, I want to get into the details. So it suffices. So yeah, by jointness arguments, it's equivalent to prove that this has. All right. So yeah, there exists a filler. So now, yeah. So now this. So yeah, again, I'll refer to Heidelberg's theory. The induced map. So you have a map that's induced. This map right here. This map right here. This one. So this map. Yeah, so it's a left vibration. So again, I think this is 2.1, but I don't remember. Right. Okay. So now, right. So because P, so right, P, let me check. Right, yeah, it's P. So now because P is fully faithful, the vibrations are contractible, right? So yeah, so again, I'll refer to HTT. So let me first write this. So as P is fully faithful, the fibers of this. But I'm not sure what I said before this. Well, I should have said fibers. Not sure what I said before this. Sorry. Yeah. Fibers of this are contracted. Right. Hence, so this is an acyclic. So yeah, I refer HTT. So it's, you can find that in HTT again. Again, I think this is section 2.1, but I don't remember exactly. Hence, it is an acyclic configuration. Okay. So now, position. So let's consider infinity categories, say C and D. The infinity categories. So a map F from C to D is an equivalent. So yeah, this kind of sums up everything. So the claim that we had before, and right. So is an equivalence if and only if it's a decay equivalence. Again, I'll refer you to Joyal's notes for the proof. It's a bit time consuming, I feel. Right. No, I think, wait. I think I can talk about it. But let me see now. I think I won't because we're already short of time. So let me not talk about that. Okay, let's skip the proof. Okay, so yeah, maybe a remark. So let me write this. So yeah, so we have so the category of simplicial categories. So that is like categories enriched simplicial sets. Simplicial categories. So let me call it scat. Admits a model structure with the weak equivalences being the decay equivalences and the vibrant objects are decay vibrations. Right. So yeah, this is called the Bergner model structure. Okay. So yeah, so it's a lot that I have to say, but right. So right. So let's go to the first slide. So I was supposed to talk about it. So yeah, I'll talk about pre-vibrant simplicial sets. Right. So okay. So let me give a definition real quick. A simplicial set, say S, is pre-vibrant if its So yeah, it's every map extends along inclusion. Right. So and for every integer between 0 and n, if so yeah, so I don't so if this is a map such that there is a constant n minus 1 simplex, then f extends similar extends to great. So yeah, examples would be I won't write it because I don't have time. The examples would be arbitrary infinity categories and right. So yeah, so the point of talking about prefibrant simplicial sets, the point of talking about prefibrant simplicial sets is so maybe a remark. That was the reason I talked about it. So if S is a prefibrant simplicial set, then for all pair of say vertices, so let me call them A, B, and S. The Khan complex. Right, then I won't prove this. And sure, an important proposition. So S is a prefibrant simplicial set if no, right, no, right, yeah, that's right. So S is a prefibrant simplicial set, and there exists an inner anodyne map as to say R such that is an infinity category. And the second point being, so the map, again, I won't get into the details of this. Maybe, yeah, I don't have the time. So let me just write it down properly. Wait, my objects are A. Yeah, I can call them X. So yeah, is an ISO for all vertices. Right. Okay. So yeah, so this one's proof is its proof is genuinely quite involved, so I won't get into that. But again, you can find that in Joyal's notes. So okay. So yeah, from the previous, from this proposition, it follows that so maybe a consequence. Let me write that as a consequence. So a map. So let me say maps to A of sorry. For prefibrant simplicial sets is fully faithful if right. So let me write it down first. Okay. Right. In the so this is the cool part. In the naive mapping space that we had talked about, right? The naive mapping space is a Yeah, let me write it down. I like to call it the naive mapping space. Mapping space is a homotopy equivalences between concomplexes for all objects. So that is a concept. So yeah, now finally we are in a position to talk about the Joyal model structure again. So yeah, the proof that I will be giving. So yeah, I'll prove that. Yeah, it's full of gaps. There are a few things that I'm not getting into, but yeah, I'll mention that for sure. So the places, the points where there are gaps, and you may be interested in that. Right. So let me start by saying that yeah. So let's recall that the Joyal model structure. Yeah, it is uniquely determined. Uniquely determined. The fact that fibrant objects. Fact that by the fact the vibrant objects are infinity categories and the cofibrations are monomorphs. Vibrations are monos. Right. So yeah, this is right. Let me write let me call this a theorem because I'll kind of give a not so complete proof with many gaps. There exists a structure. Oh, sorry, a model structure. This is a model structure. This is a model structure on simplicial sets for which cofibrations are monos, vibrant objects are infinity categories, weak equivalences are categorical equivalences. Categorical equivalences. Right. And yeah, let me add this. This model is cofibrantly generated and also left proper, I think. Yeah, I think that's right. And also left proper. So cool. So then we get to the maybe let me call it. So it's not a sketch of a proof because yeah, I do quite a lot of things, but yeah, there are kind of so there are places where there are gaps, right? So first I'll start with a lot of notation. So okay. Right. So we know that. So yeah, let me first state this. We know that the right. So categorical equivalences. So yeah. So let me call it W. Right. So that's the kind of. So yeah, that's the notation, standard notation that I use. So W of categorical equivalences. Yeah. So yeah, W is. So it satisfies. So yeah, it satisfies the 2 out of 3. So this is just kind of a reminder. So yeah, let me introduce some notation. So suppose that this is the class of monos generated by the set of maps. So I think I didn't talk about that. Okay, yeah, let me call that A. Right. Okay. Oh yeah. So yeah, we are okay defining it. Okay, fine. And F is the class of maps with right lifting property with respect to maps in A. Right. So now, now I'll use the small object argument. So by the small object argument. A small object argument, we have weak factorization system, which, yeah, so the way I had defined it. Wait, I'm sorry, is there a comment? I don't see that. Yeah, sure, thanks. Okay, so, right, so yeah, there's a weak equivalence. Weak factorization system, right? Okay, so I don't think I need to talk about the small object argument anymore. Yeah, because we're already out of time. So yeah, okay. So now let me introduce a few more things. So now let me let FW to be acyclic confabulations, C to be class of monos in the category of simplicial sets. Okay. So now again we invoke the small object argument. Small object. By the small object argument, we get a weak factorization system. Now, clearly, again, I'm a bit sketchy with things, so I'll just write out things that you can conclude, but you can check them. This works. So the way I had defined things, and therefore, right. So we want to show that CF and W. So it says, yeah, they are the distinguished classes that generate a model structure. So yeah, so it suffices to prove that this is true, right? So it suffices to prove, right? In order to get a model structure that we have, that we want. So now, okay, so there's some diagram chasing. Spoiler alert. Suppose you have a map that belongs to, wait, I'm sorry. So it's super weird, feels super weird because it's my first time using something like this. Belongs to, so wait, what was it again? Yeah, F and W, right. Belongs to intersection W. I'm sorry about that. Okay, so yeah, again, so there's a gap here in the sense that, yeah, we can prove, but I won't tell you how, because it's a bit involved, and not involved actually, but yeah, there are a few things that we need for this. Yeah, but I'll just write it. We can prove that P is an inner vibration such that, yeah, so again you pass on to the homotopy category. So this is an isovibration. And P is a categorical equivalence. Right. Then, so yeah, then we have a commutative diagram. Let me draw this. So what was it? Was it this? Yeah, I think that's right. Oh, wait, sorry. Already, no. So where UV inner anodyne, right? And G Y root T, sorry, is an inner vibration, and T is an infinity category. I should have said this before, but yeah, it's fine. Yeah, so it follows that. So it follows that Q is a categorical equivalence, which in turn implies, again, using our previous result that we proved, it's an acyclic confirmation. Right. Okay. Right. So now, okay, draw this first. Okay. So this T. Right. So in the right, so this is an induced diagram that we are getting. Right. So yeah, so the map, yeah, the map we are getting to, yeah, it is a categorical equivalence. Right. So now let me say this. Since because it is also a mono, right? So because it's a mono, it follows that so the map is right. Mono it follows that the map is bijective, right? And bijective on objects, right? Wait, let me pause for a second. Bijective on. Right. Yeah. Yeah. Bijective on object. So yeah. Follows. So from that, it will follow that it is inner anodyne. And again, this is a gap because that takes some work. Right. So inner anodyne. Let me just write. Now, since the S is an inner fibration, P is a retract. Check this of the acyclic configuration. And hence is also an acyclic configuration. Hence is also an acyclic configuration. Right. So yeah, the last thing, again, this is the third time that I'm saying there's a bit of a gap. Last thing that we need to show that the infinity categories are the vibrant objects. So yeah, I mean, it's easy, it's easy to see that the vibrant objects are in fact infinity categories, but yeah, it takes a bit of work. But yeah, you can show that, and I think I should stop here. Thanks for listening.